Today, we're going to go over standard normal probabilities. We're going to start with this problem. A university calculated that the mean combined SAT score of its new freshman class is 1,060 with a standard deviation of 120. Assuming the scores are normally distributed, determine, and then we have parts A, B, C, and D. Before I get to those, let me just give you a little bit of a background on the problem. You all know that universities tend to accept students based upon their SAT scores or ACT scores, but in this problem, SAT scores. And the combined score is the verbal part and the math part. I didn't include the newer writing or essay part or whatever they call that. We also assume that the scores are normally distributed. You could look up a definition of what normally distributed data actually means. For my live classes, I give you that definition in class. Let's take a look at problem part A. For part A, we want to determine the proportion of students who were admitted with a score between 1040 and 1190. So let's go to that problem. A normal curve, otherwise known as the Gaussian curve, looks like this. There are very few scores, in this case, that fall on the outskirts of the curve, either on the left side or the right side. When we talk about the normal distribution, we talk about these ends as being the tail. And of course, the one on the left side is called the left tail, and the one on the right side is called the right tail. Also, when we talk about the normal distribution, it tends to peak in the middle, meaning that most of the scores fall somewhere in the middle of what this curve would look like. What I have here, though, is not the standard normal curve. This is just a curve that shows that the data is normally distributed. In other words, yeah, there are a few people who got as low as a 760, maybe an 840, 900. Most students you could see scored like around here between a 960 and maybe 1160. Somewhere in there are where most of the scores are. And this curve is a normal curve, but we didn't standardize it yet. Let me explain what that is. Okay, this represents the mean, the very center of the curve and the peak point where the x value is on this x-axis. That represents where the mean is. As I have over here, we're concerned about the scores between 1040 and 1190. Here I have that region shaded, and it looks like a lot of stuff falls in that range. A couple of other things about just normally distributed data. The mean and the median and the mode are pretty much the same number. They're close enough to where we call them the same number. So what that means is half of the data falls to the left of my mean and half to the right. So for example, if I just asked the question, what proportion of students scored above a 1060? Well, that's my mean. So that would mean that half of the students, or 0.5. Similarly, if I asked how many students that were admitted to this college or university, scores fell to the left of my mean, or to the left of 1060, that would also be 0.5. We don't have a spreadsheet lookup or a table lookup that represents just any old normally distributed data. So what we do is we play around with it and we standardize it. This process is, well, it's done behind the scenes. You don't really see what you're doing when you standardize and normalize it. So for right now, let me just rehash what I was saying, that this axis represents the x-axis, and we're all the way out at 1060, where the mean is. Now, part of the standardization process is we take this center area right here where the curve peaks, and we move it all the way to the left, in this case, so that the mean lines up with 0. In other words, the mean becomes the y-axis. Additionally, what we do, and this is behind the scenes, it doesn't necessarily look like we're doing this, but this is what we end up doing. Behind the scenes, what happens is this is the y-axis, and so that means that the mean is 0. And this we convert to what's called a z-axis. Now the z-axis, for the z-axis, what we end up doing is crunching it all together, and we have a standard deviation of 1 and a mean of 0. So that's the standardization process. Let me show you what this exact same data would look like on a standard normal curve. This is what the standard normal curve looks like. As you can see, it still has basically the same shape as just any old normal curve, meaning the previous one that we just saw with a standard deviation of 120 and a mean of 1060. Then this one has a mean of 0 and a standard deviation of 1. We shifted the entire curve over so that mean became 0, and then we scrunched it together. So instead of having a standard deviation of 120, we now have a standard deviation of 1. The way this also works is instead of this axis down here being an x-axis, we now call it a z-axis. And the z-axis represents the number of standard deviations away from the mean. I already have this shaded to where it would correlate to the problem at hand, where we want to find the proportion of students admitted with a score between 1040 and 1190, and this is what the shading would look like. Let me show you how I got there. We're going to do this by spreadsheet mode, and then I'm going to refer back to diagrams as we go along. Here we are in spreadsheet mode. I already have the parameters set up. So the first parameter that I want to just type in would be my mean. Now, depending upon whether or not it represents a population or a sample, the mean could either be mu or x bar. It doesn't really matter at this point, so we'll just type in the mean as is. The mean was 1060. The standard deviation on the original problem, 120. And for the first part, or part A, we're only concerned about the proportion of students who scored between 1040 and 1190. So In a problem such as this, we have two x values, and one of those in this case would be 1040 and the other one 1190, because that's what they are on the original normal curve. Because we're doing a conversion from an x-axis to a z-axis, and that's what really does all the work, and that's the behind-the-scenes work, what we do is we use the z conversion formula, otherwise known as finding the z-score or the z-value that corresponds to this x value with a mean of 1060 and a standard deviation of 120. It's a subtraction and a division. Basically, we take our x value, we subtract the mean, and then we divide that result by our standard deviation. You have to put the entire numerator inside parentheses. We have equals, open parenthesis, x value. Now, if I drag and drop down, do I want that to change? Yes, so I'm going to leave it just the way it is. Minus my mean. And that one I always want to be drawn from that particular cell. So I am going to put my dollar signs on that. Now I close parenthesis, divided by my standard deviation, and that I always want it to be called from that cell. That's a static cell reference. So I'm going to add my dollar signs to that and press enter. And now I'm going to do the same thing for this x2 value. That's the hardest part of the whole problem. The rest of the stuff is stuff that back in the day we would just look up on a table, but you all have this already in a spreadsheet. We're going to come to this part in just a minute. I just want to point out what these values now mean. Remember, we have an x value of 1040, and that corresponds to a z value of negative 0.1666667. Here we have an x value of 1190, and that corresponds to a z value of 1.08333338. Before I go to the diagram also, let me explain something that hopefully will make sense to you. If I take a look at 1060, and remember, I brought that 1060 all the way down to 0. I just shifted the whole curve over. Since 1060 is 0, and here I have an x value of 1040, my question, or the question you should be asking yourself is, does this negative z value make sense? And the answer is it should, because 1040 is to the left of 1060, just like negative any number is to the left of 0. Similarly, here I have an 1190, which is to the right of 1060, which means my z value, this value right here, should be to the right of 0. And it is. Let's go back to the diagram. Here we are at the diagram. Take a look on the diagram. Here is 0, and just a little bit to the left of 0, that's where this line of the shading is. So that's negative 0.1666 whatever. And the other x value turned into a z value of 1.083333, which is approximately right here. And now we're concerned about the area that's shaded in between these two. The spreadsheet will only give me values to the left. In other words, if I just pop in, say, this z value, and I want to know how much area is under the curve, it will give me the area from here, or the proportion from this all the way down, all the way into the tail, the left tail. And if I did the same thing for this z value, I want to know the area or proportion. I'm going to use those interchangeably. It means the same thing. It will give me from this line right here, and it'll give me the entire area or proportion all the way down into the tail. One thing that I forgot to mention that's extremely important, the standard normal distribution, because it is a probability distribution and it's a continuous probability distribution, the entire area under this curve, the entire area is 1, meaning 100%. Let's go back to the spreadsheet to see where this takes us. Here we are at the spreadsheet. I now have a z value of negative 0.16667, etc. For this problem, I'm going to first find the area to the left of 1.08333333, etc. And in order to do that, I simply use equals. There's a built-in function within Excel that will give me the area that falls to the left of this z value, all the way into the tail of the Gaussian curve, otherwise known as the standard normal curve. And that function is norm dot s dot dist for distribution. Norm dot s dot dist. And what we want to do is first click on our z value. Now remember, I'm going to use the second one first, and there's a reason why I'm doing that. It's because the diagram, just the way I set it up on the diagrams, I did this one first, so I'm going to do it first here. So first thing it's asking for is the z value, comma, and now it's asking me whether or not I want that to be cumulative. And the answer to that is yes. Unlike the binomial distribution, this one, or the standard normal distribution function, it will always be true that we want the cumulative value. And I close parenthesis and I press enter. Let me go back to the diagram. In the diagram, this is what that would look like. Here I have a z value on the z-axis of 1.083333, and the value that the spreadsheet will give me when I look up the area to the left of that is this entire proportion. Let's check and see if that will make sense. I did mention earlier that half of all the data falls to the left of my mean, and in this case my mean is 0, and half falls to the right. So if I just asked you to guesstimate, give me an approximation of how much data is shaded in or what the proportion is to the left of this 1.08333, you would hopefully guess it's more than half, because just from the tail on up to this value, 0, would be half of it, and then this is actually a lot more. So if I were to guess, I would guess that it's something around, I don't know, that looks like 80% of the data. I'm not 100% sure. It might be a little more than 80% of the data. Let's go to the next diagram because I have the value put in over there. Here you can just see I have an x2 or an x value of 1190, which corresponds to a z value of 1.083333. And now that corresponds to an area to the left of z of, well, I kind of got it right. It was more than 80%, and that worked out to be 0.8607-ish. And if you take a look at this, that means that this represents about 86% of the data fell to the left of this z value, which, if we went all the way back to the original diagram, it would mean that about 86% of the students accepted scored less than an 1190 combined score on their SATs. Let's go to the x1 value. We would type in the same thing, equals norm.s.dist. Click on the z value, comma, do we want it to be cumulative? Yes, because the norm.s.dist is always going to be cumulative. Close the parenthesis, press enter, and what this is saying is that approximately, 43% of the data will fall to the left of negative 0.16667, blah, blah, blah. So let's go to the diagram and see what that looks like. As you can see on this diagram, we are to the left of 0 for this z value that corresponds to an x value of 1040 when you have a standard deviation of 120 and a mean of 1060. So this z value right here, now let me ask you this, if you were to guess as to whether or not this number would be more than 50% or less than 50%, I hope you would guess that it would be less than 50%. Why? Because 50% of the data falls from all the way out here in the tail on up to this 0 right here. Well, we have this little piece that's missing right here. So what that means is that it has to be less than 50%. I don't remember exactly what it was on the spreadsheet, but the next slide should tell me. And there we go. It's about 43.38%, or 0.4338 is the proportion of data that falls to the left of negative 0.16667. Let's go back to the spreadsheet and confirm that that's true. Yes, that's what it is. Now, as I said, we have an area to the left of one z value and an area to the left of the other z value. And how would we get the area in between these two, or these two z values, I should say? In order to get the area between these two z values on a spreadsheet, we simply subtract one area from the other. Meaning, here I have a larger area of roughly 86%, and here I have one of roughly 43%. So, in this cell, where I have it labeled as area between, we would say equals, click on the larger area, minus the smaller area, enter. Going back to the original problem, the number of students scoring between 1040 and 1190 at this particular college, which had a mean of 1060 and a standard deviation of 120, we know that the proportion of students that scored between these two values is approximately 42.68 or 69%. Let's take a look at the diagram. Okay, so what we have, the area to the left of the x1, then z1 value is 0.4338. We know the entire area to the left of 1.083 ended up being about 86% or 0.86. If I take this entire area to the left of this and I subtract this area right here, well, I pressed on it by accident. Let me go back. And I subtract this area here, I will be left with only the area in between. In other words, the area in between any two z values is one of the areas minus the other area. So in this case, it's going to be 0.8607 minus 0.4338. And that gives me an area of 0.4269, which I already put in here. In other words, if I added this area up plus this area up, I would get back to that 0.8607. So let me physically subtract this area, and maybe you could see it better. There we go. The area in between ends up being 0.4269. Meaning the proportion of students who scored between a 1040 and 1190 at this university was about 42.69% of the data. And by the way, notice I'm expressing my answer in different ways. I could also express it just saying, what is the probability that a randomly selected student scored between a 1040 and 1190, and you would just say the probability is 0.4269. If I asked for this as a percent, you would have to convert it to a percent, meaning that you would have to move the decimal point over 2 places to get 42.69%. No, that's not going to be too difficult for you, just wanted to point that out. Let's go on to the next problem. So B is asking for the proportion of students who were admitted with a score between 860 and 1030. Let's see what that looks like on a diagram. This is what the original just normally distributed data diagram would look like. 860 is right here. 1030 is right here between 1020 and 1040, and this shaded area would represent the proportion of students that scored between those two scores. Let's take a look at how that would translate to a standard normal curve. And on a standard normal curve, this is what it would look like. We would want to know the area in between this value and this value, and I'll show you how to get to those two values. Let's go to the spreadsheet. For this problem, the mean and standard deviation are the same. I'm using the same problem, and I'm just asking you different pieces of information off of that original problem. Keep in mind that on any problem, you would have to update your mean and standard deviation, and that would have to be given to you in the problem in order for you to do the problem. So this one, or problem B, asks for scores between 860 and 1030. A score of 860 translates to a z value of negative 1.666667. An x value of 1030 translates to a z value of negative 0.25. Let's see how things go. All right, so this z value, all of the area to the left, or the proportion of students that fall to the left of this z value, is 0.4779. And area to the left of this z value is 0.40129. Now, in order to get the area between these two z values, or the proportion of students that scored between an 860 and a 1030, what we do is we subtract these areas just like we did before. Now, normally I would just leave this on the spreadsheet, but I took it away just to re-emphasize exactly what I'm doing. I start by typing equals, click on the larger value, minus the smaller value, and press enter. And there we have it. We have an area in between those two of roughly 0.3535. Let's see what all of this looks like on a diagram. On the diagram, the 1030 SAT score corresponded with a z value of exactly negative 0.25. And the area to the left, all the way into the tail of a z value of negative 0.25 is 0.40129. Then the other z value corresponded to an area of approximately 0.0478 into the tail. And if I subtract this area right here, in other words, the 0.0478 from the entire area to the left of this blue, or the entire area that was originally in blue, I would have 0.4013 minus 0.0478, which equals approximately 0.3535. Let's see what that looks like. And there we have it. The area in between these two z values, which came from my original x values of 860 and 1030, with a mean of 1060 and a standard deviation of 120, we now know that the proportion of students that fell in this area is 0.3535, and that's what that proportion would look like. Let's go to Part C. Part C wants to know the proportion of students who were admitted with a score that fell below 830. Notice there are not two x values here. There's only one x value, and that one x value is this 830 right over here. Let's see what this looks like on a normal curve. On the original Gaussian curve, with a mean of 1060 and a standard deviation of 120, and we want to know the area to the left of 830, meaning all the students who were admitted that fell below a score of 830. Let's go to the spreadsheet to see how that translates to z-values and areas. We want to find out the proportion of students whose scores were below 830. So I'm going to type in 830. Just press enter. Now, there's no x2 value in a case like this. An 830 corresponds to a z value of negative 1.916667. And the area to the left of that is 0.02764, etc. Now, that's basically it. we don't really have to go any further than that, because this means the area to the left, or those that scored below the z-value, which came from an x value of 830 when the mean was 1060 and the standard deviation was 120. So if I were to answer this question right now, my answer would just be 0.0276. Keep in mind, I could ask that as a percent, so that would be 2.76%, or I could also ask that in a different way. For example, I could ask, if a student is randomly selected, what is the probability that that student scored below an 830? And no matter what, your answer would be the same. It would be 0.0276. Let's take a look at the last part of this. Part D wants to know the proportion of students who were admitted with a score that fell above an 1100. Now, this is just slightly more difficult than when we say below. You just have to remember a few things. Let's go to the Gaussian curve that represents this. Here we are at the Gaussian curve that represents problem part D, those that have a score that fell above 1100. Two most important things you need to remember is that on the standard normal curve, the entire area underneath is 1. Why? Quite simply because it's a probability distribution. And in a probability distribution, if it were discrete, the sum of all probabilities would be 1. Well, this is a continuous distribution, which we think of more in terms of area. And that means the entire area under this curve is 1. Now, once we know that, the rest should be easy. But we also have to keep in mind that whenever we get an area for something, for any designated x value or z value, we are always finding the area to the left. So let's go to spreadsheet mode, and I will explain this in the two different ways. One, just crunching the numbers, and two, with the diagram. Now, keep in mind, there's only one x value for this problem, and that x value is 1100. That 1100x value corresponds to a z value of 0.333 repeating, and the area to the left of that is 0.6305 or 0.6306. Let's just take a look back at the diagram, and then we'll come back to the spreadsheet and I'll explain this in better detail. So according to the spreadsheet, the z value with an x value of 1100 was positive 0.3333 repeating, and that is represented by this like magenta line right here. And the area to the left of that from the spreadsheet was 0.6306. We know that the entire area under the standard normal curve is 1. Since we know the entire area under the standard normal curve with a mean of 0 and a standard deviation of 1, the entire area under that curve is 1. I know that if I subtract this reddish area right here from 1, I'll be left with only the area towards the right tail. In other words, area to the right of Z1 would equal 1 minus the area to the left of Z1. Or, in this particular case, 1 minus 0.6305586 ends up being 0.3694. Now, let's see what happens when I physically subtract this reddish or pinkish color. Magenta. We'll go with magenta. And there you have it. We are left only with 0.3694 as the area to the right of the z-value of 0.333, which in this case corresponds to an SAT score of 1100. So let's go back to the spreadsheet, and I'll just show you how to do that on the spreadsheet. On the spreadsheet, we simply do this. We only had one x value, that was 1100. That corresponded to a z-value of positive 0.3333, repeating, which corresponded to an area to the left of 0.6306. Well, over here, if you see, I already have this on the spreadsheet. Area to the right, I'm going to just retype what I already have. That equals 1 minus the area to the left. And that gives me that 0.3694 number. So it's that simple. When you only have one x value, which corresponds to one z value, you could ignore this whole x2 and area between stuff. Just work with this top line right here. Okay, we're done with the standard normal conversions.